Welcome to Brain Vision.
In this problem, we're looking at a heat lamp that emits infrared radiation. And that radiation is directed at a person's leg. So here's this person's leg, and it's directed over an area, certain area, with a radius r equal to 4 centimeters. And they're going to ask us a few questions about this. The first being, what's the average intensity of that infrared radiation? Well, if you recall, average intensity is equal to C epsilon naught times the root mean square of the magnitude of the electric field. They've told us what ERMS is. ERMS equals 2,800, and that's newtons per coulomb. And we know what C and E are. Those are our constants, C being the speed of light, and epsilon naught is the permittivity of free space, or the vacuum permittivity. 8.85 times 10 to the minus 12. That's units of coulomb squared per Newton meter square, if I recall correctly. And then just plugging all of this in, this is squared here, the ERMS squared for our average intensity. Plugging all of that in, you should get that the average intensity is equal to about 2.1 times 10 to the 4th. And that is watts per meter squared. And that's the answer to part 1. Now in part 2, we're looking at this radiation focused on the person's leg and what's the average power that's being delivered to the leg. So now we're looking at average power. That's equal to the average intensity times the area over which that's being spread out. So we know that the area of a circle, so area is just pi r squared. Thing to keep in mind though is that all of our units so far have been using meters, so we want to convert from 4 centimeters into meters. R is then 0.04 meters because we just divide by 100. And so plugging that in over here for the average power, get 2.1 times 10 to the 4th watts per meter squared multiplied by pi times 0.04 meters squared. And then plugging all of that in, we get a power that's about 1.1 times 10 to 2 watts. And that's how much power is being directed to that leg. Now, we know that the portion of the leg that is being irradiated by this infrared radiation, so just that little portion inside the circle there, that has a mass 0.28 kilograms and a specific heat capacity. So this is, how much energy it takes to heat it up. Its specific heat capacity, C, is 3,500 joules per kilogram degree Celsius. So what that's telling us is that it takes 3,500 joules to heat up every kilogram of this mass by 1 degree Celsius. So if we use that, we can see that C times the number of kilograms times the change in temperature, the number of degrees Celsius that we want to increase it by. That's going to be equal to the power, how much energy we need to deliver to it, multiplied by the time. So however many seconds this power needs to be applied in order to raise the temperature by that much. So I'll go ahead and let me scroll down a little bit here. There we go. We can go ahead and just start plugging things in for this. We've got 3,500 times the mass times the change in the temperature, so just 2 degrees Celsius. And all of that is going to be equal to this power multiplied by the time, T, which is what we're trying to look for. How long does that power need to be applied to the leg for its temperature to change? Well, divide by the power on both sides of that equation. And we get that T is equal to about 18 seconds.